Okay, that's a song by a group that was very famous in the 70s. I think they're still active, by the way, called Chicago. And the title of the song is Does Anybody Really Know What Time It Is? So that's exactly the purpose of this talk. And now it works. Okay. Oh, cool. Okay. Uh, First, what do we have in most languages? In general, you have some clock function, and all the language standard says is, well, you got what is returned by the operating system. So it means that you have no guarantee at all, but what kind of time is returned by those functions. When you, in every language, you have a delay or sleep or equivalent functions, and in general, the standard says that it is approximate. How much approximate? There is no guarantee about how long you will actually delay. For casual software, that's not a big issue, but when you're talking about real time, that can be a big issue. Note that, for example, in C, you have a delay in nanoseconds. Why? Because those people have no fixed point. So they take, someone thought that 1 nanosecond was accurate enough and that nobody would ever need more than a nanosecond. Okay. So in Ada, of course, as usual, we do it better. Some definitions. What is time? Difficult to define actually. Well, it's something that varies during computation. That's almost all you can tell. And it's the value returned by what is officially called a time base or a clock. So you ask, what time is it? And that's the answer of a clock is time. Note that for computers, time is not continuous. In general, you have jumps, and a clock stays at a certain time and then jumps to a different time. On the other hand, a duration is a certain interval of time between two times. So it's very different. It's a number of seconds between two times, not necessarily integer, of course. Real time, I like to remind, although it's not exactly the same thing, what is the definition of real time? It means that the time taken by computations is a requirement. I mean, if it takes too long, the result is wrong. I mean, if you invert a matrix, if it takes a long time to invert the matrix, the result will still be correct. If you take half an hour to call for the fireman, then the result is wrong because the house has burned. Okay? So it does not necessarily mean that it's very fast. I mean, if you are watching the drift in the San Andreas Fault, if you take one sample every day, that's enough. But if you stay 1 month without taking any sample, then you can miss an announcement of an shape. And a raised condition, because I'll use that also later, is a condition that happens under very precise conditions of timing and especially never happens during testing. Okay. Just to give you an idea, if you have a probability of something happening once in a million in a 1 second loop, it will happen once in 11.5 days. So you won't let your software run for days and days and how much longer, okay? I was once in an investigation, it was demonstrated that the software would fail after 4 years of continuous execution. You cannot test it for 4 years, okay? Yes, it was a kind of timer overflow, but very, very fun. So, what time do we know in the real world? First, the only real one is called TAI for International Atomic Time. But you know, the International Office for Time is located in Paris, so that's really le Temps Atomique International. That's why. So this is an absolute time, not related to Earth's rotation. It's the official basis for all the other times. Okay, if you are, as I said, timing. If you are programming a lunar probe, you don't care about the rotation of the Earth. So that's the real universal time. To give you an idea, this is defined by the International Bureau of Time by atomic clocks that have a drift of 1 second in 100 million years. Okay, so they're incredibly accurate. Then you have UTC. We have a problem with the rotation on the Earth that causes leap seconds. I'll explain more in detail soon what are leap seconds. Sometimes you add a second to the time to compensate for slight variation in the speed of Earth's rotation. Currently, UTC is the same as TAI minus 37 seconds. So it means that if you ask a TAI clock, what time is it? There will be a difference of 37 seconds to a clock that is UTC. That's the only difference between the two. TAI does not insert leap seconds. Then we have legal time, which is the one you use generally on your watch. So it's sometimes called wall clock time or local time. Of course, it depends on the location and it depends on the time. So the time depends on the time, okay? That's because you have some daylight saving time and winter time. And sometimes you have sometimes that do not exist or sometimes that exist twice. So that's very unfortunate when you are talking with computers, of course. And then sometimes you are interested in CPU time, which is not really a time, which is a time spent by a task in while owning the CPU. So there are all quite different definitions. A word about these leap years and leap seconds. The real duration of a year is that 365.2422 days, which is close but not equal to 365.25. So we add, as you know, a day on the 20th of February every 4 years, except for years that are multiple of 100, except for years that are multiples of 400. So 2000 was a leap year as an exception to the exception, okay? And there is also a small correction every 4,000 years, but we can ignore that for the moment. You mean? That exception hasn't been applied for. No. Well, if you made astronomical calculations, well, but then you use TAI, so you don't care. Leap seconds are something more difficult. The Earth has some irregularities in rotation. For example, a number of meteorites fall each day on the surface of the Earth. So it makes it a little bit heavier. And the momentum is conservative, therefore it slows down the Earth. I think also that the melting of the ice has an influence on the rotation of the Earth. Some are more or less deterministic, but it's actually very hard to predict. So, what is called a leap second is added either between the 30th of December and the 1st of January, or at the end of June. And sometimes the International Bureau of Times decides to add 1 second. I think there has been some times where they even subtracted 1 second because there are various reasons of irregularity. So that second, the official name of that second is 23 colon 59 colon 60. But in ADA, we have a subtype second number that ranges from 0 to 59. So that 60 would cause a constraint error. So there is the leap seconds in ADA are treated specially. So you have the time and you have a number of functions that return in addition the number of leap seconds. For example, if you take the difference between two times, because you cannot express that as a number of seconds. Of course, you have tables of past leap seconds, but if you are computing a date in the future, they are ignored because we don't know. Okay. They cannot be predicted. Now, the issue of time zones. So a time zone is defined, at least for the purpose of ADA, as an offset given in minutes between UTC and your local time. In minutes, because the seconds are always the same. Okay, you don't have differences in seconds for time zones. But it's not necessarily a number of hours. A certain number of places on the Earth have a shift of 30 minutes. I don't think there is more. Some are 15 and 45 exist also, maybe. I have seen in the annotated reference manual, I think the maximum difference between two time zones is something like 26 hours for various reasons. So a time zone depends on the place on the Earth, of course, and also on time, because you have that daylight saving time and winter time. So you must understand that the change between winter time and daylight saving time is taken as a change in the time zone. It's not the time, well, you have a different time zone. So think of it, it's like if you carry your computer, if you take the train here in Barcelona and you go to Lisbon. What happens to your computer when you cross the border between Spain and Portugal? Okay, you have 1 hour difference. That's what happens when you switch the time zones. So most of Europe is on what is called CET, UTC plus 1 in winter, except UK, of course, UK never does it like the rest of Europe, and some countries. So Portugal is really to the west, so there had to be UTC, and some countries far away to the east. So I said that. So the daylight saving time is a different time zone, and it changes normally on the last weekend of March and October. Also, we have a problem that it's not some countries extend over several time zones. I think Russia is the country with the most time zones, 7 or 8 time zones. It's really extends. It's really huge. So, how do we deal with all these issues in ADA? So, we have in ADA what is called time types. Note that an implementation may provide several time types. The compiler knows that certain types are time types. For example, ada.calendar defines the type time, and it is by definition a time type. Okay? The time base, the clock associated to this time is implementation defined. Okay? I remind you, uh, implementation defined means it can vary from an implementation to another one, but it must be documented. Implementation dependent, you don't know, but implementation defined, the documentation must tell you what clock it is, which clock it is. And we have functions that define time zones, and actually the time base is related to an implementation defined time zone. Okay, and same thing, you must be told what it is, but you don't know in a portable manner which time zone is used by ada.calendar. And you have a function called clock that returns a value of type time. Time is a private time, okay? So you don't know how it is represented, and we have accessor functions that deal with time. You have a constant in system called system.tick, which is defined to be the minimum variation of time. I told you that the time was varying in jump. So you know that if you have two calls to calendar, that clock, they will not differ by less than system.tick. So you cannot measure a time, a duration less than system.tick. But that's defined, at least you have the information. You may have other time types connected to other time bases. The idea is that in an embedded system, well, you have a clock on your standard board that may not be accurate enough for your needs. And you can have a special clock board in the back plane of your computer that give you a better clock. So normally, well-behaved compiler should provide you with a package that corresponds to that clock, and the compiler should be informed, I don't know how, that this is a time type, and every time-related function that uses that type will be related to the corresponding clock. So the idea was to be able to have hardware clock and to be able to use them the same way as the standard clock. So what packages do we have in ADA? Standard has the type duration. Duration is a fixed point type. I'll explain that a bit later. We have minimum constraints on duration. In other languages, it just implementation dependent. Here, you know that duration will cover at least 1 day, and the difference between two values must not be greater than 20 milliseconds, which is quite coarse. Of course, if possible, it can be much better, but it cannot be bigger than 20 milliseconds. But be careful that a day can be longer than 86,400 seconds, for example, when you switch the time zone. It can be shorter also. Uh, I had already prepared that presentation when I was personally hit by a bug due to that, where I was scanning through the year, and the 26th of March was disappearing. Because the 27th of March, less 1 day, well, midnight on the 27th minus 1 day brings you at 11 p.m. on the 25th, because that day only had 11 hours. Okay, it was a change. Longer or shorter, but of course sometimes you will have a constraint error if it's longer. ADA.calendar so provide the time function and a function that translate time into something that's more human readable, year, month, day, second, but according to a time zone that is implementation defined. So it should be documented. In general, compilers do the right thing. It's the local time, okay? But you must be aware that this is not formally guaranteed. You have various functions to convert between a date in year, month, days format and and an abstract time, but always relative to this implementation defined time zone. There is no provision for leap seconds in that package. Okay, that the original package from EDA 83, and people didn't care about that problem at that time. There is also a plus and minus, adding a or subtracting a duration from a time, but the meaning of these is not obvious if you are changing time zones in the middle, especially with the light saving time. Okay, so in a sense, EDA calendar was not sufficient if you want to deal precisely with those kinds of issues. So, starting 95 or two, I don't remember exactly when those packages were added. It was necessary to make better packages dealing with time. Time zones define the type called time offset. And actually, you don't have the name of time zones. You play with time zones as a number of minutes. Okay, so you define the number of minutes of difference to UTC. So you have a function called local time zones that gives you your local time zone, the time zone where you are, as a number of minutes. And the funny thing is that it has a time parameter. You must give it a time to get the time. Once again, because the time depends on the time, okay? Then we have a package called ada.calendar.arithmetic that give you operation between a time and day count. So that allows you to add or subtract a number of days from a given time. It's not clear that what is a day? A day is an integer type, okay? Is it equivalent to 86,400 seconds? Or is it one less day in the calendar? This is not defined, and I may write an AI on that topic because it's not defined. Because I was beaten by that problem recently. It gives you also the difference between two times as a number of days, of seconds, and of leap seconds. Because the number of seconds is given as a second number, it cannot be 60. So we separate the leap seconds from the regular seconds. And then you have ada.calendar.formatting, which in a sense is like calendar made right. We have seen that calendar did not deal with a number of issues. So it uses the same clock, the same time base as calendar, but it has the same kind of operation as calendar, but there is an extra parameter called time offset that gives you the time zone as a number of minutes from UTC. So this time you can specify various operations and specify either your local time offset, if you wish, or by default it's 0, which means that all operations are made assuming that the time is UTC. You also have some versions with an extra parameter where you can give a number of leap seconds to account for between those operations. You'll read the specification of the package if you're interested. So, as I said, the default time offset is 0. It gives you some operations to retrieve the day of week, Monday, Tuesday, and so on. Well, it's easy to do, but it's better if you don't have to rewrite it yourself. And even, guess what, formatting functions, okay? Although it's called ada.calendar.formatting, it has more arithmetic function and, well, it gives you formatting an image function that returns a string with a well-defined format. It's year, must be year, colon, day, colon, well, colon month, colon day. No, dash. It's a dash, and then hour, minute, second separated by colon. Well, the format is very precisely defined, so it's easy if you want a different format to extract the various species and reformat it any way you want, and value that does the opposite, that takes up a string and decodes it appropriately. For compilers that support Annex D, but that's most of the compilers, you have a package ada.realtime. That realtime is a time type as defined by the standard, and it's a different time type. The idea is that it's a time that's just defined as a number of seconds from an implementation defined starting time called the epoch. Okay, this is not necessarily the same as Unix epoch. Some compilers just start the time at 0 when you start your program. Okay, we don't know where is the time 0, but it is a time. It is a time type. Therefore, a delay until can be based on that, and it is guaranteed to be non-decreasing, which is not the case for the whole clock time, of course. There is an equivalent to duration, but it's called here time span, and also a tick constant, which is the minimum variation between real time dot time. And, well, same thing, various arithmetic operations operating on that. And because you have conversion function from duration, including sub-seconds, that is partial seconds. Some child packages provide extra operation like timing events that can initiate a callback, a pointer to a procedure that will be called, like for interrupts, at a certain time given in real time. You also have a package that manages execution time. So it's relative to each task, and there is, is it called clock? I'm not even sure, but it's the time spent by the task within the CPU. Note that this one is not a time type. You cannot delay relative to CPU time, because if you don't have the CPU, well, the time stops for CPU time. Okay, so it is not according to standard time type. And you also have some operation like split time off and so on. Some child packages used by sophisticated scheduling algorithms. So a timer can trigger an interrupt when you have consumed all your CPU time. You have algorithm called budget scheduling, where you give a certain number of seconds to a task. So when the fuel is exhausted, you have a timer which is triggered, and then you can switch to another task or give it a little bit more or do whatever you want. And you have a full theory of scheduling about that. Or you can have group budgets, that is when you give a certain amount of CPU time to a set of tasks and so on. You have papers by Burns and Wallings, of course, on all those scheduling algorithm. Interrupts tell you how much time you wasted handling interrupts. A word now about duration. First, you must know that a duration should never be implemented as a floating point. Fortunately, in Ada, we have fixed points. I'm a big lover of fixed points. It's another way of representing non-integer numbers. In other languages, as soon as you have a point in a number, it's a float. Okay, but you have many representations possible for non-integer number, and especially for duration. Well, duration in Ada is a fixed point type. Because see what happens. In a floating point type, you have the delta x over x, which is constant, which means that as the time grows, the values that can be represented stretch. They are farther and farther away. So imagine you have a loop with a constant time. After a while, well, I should not, may I point with, yes, this will be visible for the remote people. In the beginning, you waste a number of represented values that are not used. You jump over them. And as the representable values stretch, after a while, you do not reach the next possible value. And you run down and the time stops. So you are limited in the number of iterations, for example, over simulated time, that you can do by that phenomenon. If you have a fixed point type and you adjust it, for example, to the duration you want, you may have as many loops possible as allowed by the number of bits. Okay, so that's very important. And well, there was a famous accident during a war in the Near East. There was a battery, an anti-missile battery, programmed in C, and the duration was represented as floating point types. And well, the people who wrote the software knew about the issue, and there was a requirement to reboot the system every day for that reason. Now, if when you are a soldier, you have a system that seems to work perfectly, you fear missiles to come on you, and you are asked to reboot the system, well, they just didn't do it. And there was a missile that was missed due to that increased loss of accuracy for that reason. When we want to wait for a while, we have the delay statement. So the delay statement is expressed as a duration. So from our type standard.duration, expressed in seconds, but of course it's a fixed point type. It's not necessarily an integer number of seconds. I told you that. And sometimes you want to wait until a certain time. In EDA 83, it was the only delay that we had. So people who wanted to wait until time t would write something like that. We have a minus operation between two times giving a duration, delay t minus clock. Okay, that's the number of seconds between t and now. And this is a typical race condition. This is what happened, what can happen, very unlikely, but it can happen. First, you compute t minus clock, say 2 seconds, okay? And between the time where you compute that difference and when you enter the delay, you are interrupted by a higher priority task. Very unlikely, not impossible. And say that this task runs for 5 seconds. That's okay. It's of a higher priority task, so it can preempt a lower priority task and waste some time for it. But then you re-enter your delay with the time that was computed before, and although the wake-up time has passed, you will still wait for 2 seconds. And this is not acceptable. And there was positively no solution for that in EDA 83. By the way, when they designed Java in the 2000s, so that was 17 years after that problem, and they made the same error. So in EDA, starting in 95, we have the delay until statement where the wake-up time is given at a time and not a duration. And this one has no problem. Note that the time can be any time type. It can be, of course, the calendar.time, it can be real-time.time, or if you have a special board with a clock on your computer, you can make it relative to your high accuracy clock. And in that case, you can say that there is no race condition. You can be interrupted at any point in time. Since it's an absolute time, you will not, there is absolutely no race condition. So if you are really, if you are just programming some game and animating flying folders or things like that, so of course you can use the delay. But as soon as you are serious about your delays, you must use the delay until. Now, the delay is never exact because, as I said, time varies in jumps on a computer. If you are conformed, there are two important properties of the delay statement, whether delay absolute or related. First, a task is never reactivated before the computed time. So it can, if you give a time to wake up that falls, say, between two hardware ticks of your clock, it must be rounded up. It cannot be rounded down. So you cannot guarantee an exact delay. That would mean nothing, of course. But at least you are guaranteed not to wake up earlier than the expected time. And if you are conformed to Annex D, there is a model of delay here. So the blue line, here is the perfect delay. You can ask for a negative delay, but a negative delay means don't wait, okay? So ideally, for a negative delay, you get 0 delay. And for a positive one, the actual delay is equal to the requested delay, okay? But in practice, since the time varies in jumps, what happens is that, well, even for a negative delay, it takes some computer time to realize that it's negative. There is at least an if statement somewhere for that. So you still spend some time even for a negative delay. And then, because you have to wait for the next tick, it means that your delay will vary in jump. You will never pass that line, okay? So up to that line, you'll get a fixed time, and then the actual delay will vary in jumps like this. And this defines an envelope for the maximum difference between the requested delay and the actual delay. If you are conforming to Annex D, you must document that envelope. So T1, which is the minimum delay that you will have, and T2, which is the maximum difference between the requested and the actual delay. So in that case, you also have an upper bound to the difference between what you request and what you get. So in practice, some recommendations when you are dealing with time, you say that the issue is far from obvious. Use calendar only for casual usage. I mean, if you have a normal program, you just want to display the clock somewhere, calendar is fine. Otherwise, use calendar.formatting. Because you never really know what happens with those time zones, I would say that during computation, keep all your times as UTC, because UTC never varies. Okay, it's a safe um, it's a safe basis. It's a problem, for example, with file timestamps. Maybe you have experienced that. I never had the answer whether the time that you see when you ask for the properties of a file, is it UTC? Is it local time? Is it local time it was when the file was created? Or is it changed according to the current time zones? When you want to synchronize two machines, and especially one with Linux and one with Windows, suddenly the timestamps of the files have 1 hour difference. You need to adjust them. So as long as you are UTC, you're safe. You will use time zones only when you want to display something for the real user. 3 minutes? Yeah, that's fine. That's fine. And don't use the operation in calendar. Take the ones in Ada calendar arithmetic, Ada calendar that formatting, where you can choose the way you deal with time zones. Of course, always use delay until. And if you are really picky, be careful with leap seconds because it's a difficult issue. And in a sense, you can get them and provide them because nobody knows how to really deal with that issue. So it's up to you to decide. That's it.
Perfect timing.
Thank you. Well, I had to.
So, other questions? Yes, we have one.
Well,
Thank you very much for very informative presentation. I have a question about something that you said about the ADA real time height that is guaranteed to be non-decreasing.
yes.
So coming from the world of microcontrollers, I worry about wraparound. So if the time is absolute and non-decreasing, eventually will wrap around. So how it will become, it will be like if it's decreasing because the current time will be like smaller than the older time because of the wraparound. So
I will respond only in presence of my reference manual. But it's a private type. So my wild guess is that maybe after certainly a very long time, you may get a constraint error. I see no reason for, well, formally, I think it could be internally represented as a modular type. But yes,
the implementation requirement for real-time time is the implementation requirement for real-time time is from program started and 50 years later.
yes.
So if you have a time on 50 years or more, you may run into a problem. So you have to respect that upper bound, and it's a requirement.
So since this was added in 95 or later, up to 49, 59, something like that, you're safe.
I just wanted to say that I'm looking at
A reference manual.
implementation and its duration. So it won't wrap around. It will eventually strengthen.
So it will crash there because it will cause a runtime exception.
I think that having an exception is better than wrapping around. In both cases, the results are wrong, but with an exception, you know it.
You can reboot.
You can reboot, you can, well, if it's really a safety critical thing, you have to care for unexpected events in any case.
You can catch it.
You can catch it, you
If
can.
catch it, you know. But it doesn't run.
No. Wrapping around is really the worst option.
Another goodness of ADA.
Mhm.
It won't be possible in C.
In C, it always wraps around. Well, no, I even think it's not defined by the standard. What happens in the case of an overflow of integer types. Most of the C compiler do wrap around, but I'm not sure it's required by the standard.
It's required for.
Well, you know, the goal of C is to have access to the machine. It's a low-level language. It's the best of the low-level languages. And the goal is to do as the machine does. So from a C point of view, it's very logical to say it's defined by the behavior of the machine. You want to access the machine in C. Of course, in ADA, we want to abstract away from the machine. That's it?
Do
We have one
time?
question
Yeah.
online.
Yeah.
Hello?
Yes?
Please go ahead.
So, question from Luke. Say I need to add a new time package for a custom hardware device. How does the compiler know how to use it? Does it use name equivalence here? Can it use non-RTS based time type?
Ask your friendly vendor. I mean, other time types are implementation defined, so I don't know, you may have a pragma to define something as a time type or other mechanisms, depends on the compiler. For embedded system, I would expect a compiler to provide some mechanism, but that's too low level to be standardized.
Hopefully that answers the question. Is there another question online?
No, that's it.
Okay, then we are right on time.
Okay, thank
it's
you.
3:30. So perfect. Thank you.